All right, so welcome back. Last week we started on functions, and that's where we're going to continue today. I will remind you that we are on Piazza and we are on YouTube, so if you have any questions, please go ahead and post there. Otherwise, we left off... sorry about that. We left off last time by talking about how to modularize your code. I gave you a demonstration. Let's just make sure that everything's working still. Oh no. Okay. Oh yeah, it should be working. If it's not working, please let me know online, either on Piazza or on YouTube. Anyway, to get back to where we were. I gave you a demonstration last week where we modularized our code. We created our own libraries, essentially. Remember that the standard input-output library, stdio.h, the math library, math.h, those are all separated out into separate files so that you only have to bring in a small subset of code that you're actually going to use. The way that we did our code is I separated all of the documentation along with the prototypes out into a header file. That header file ended with a .h, just like stdio.h and math.h. Then the definitions of the functions went into a separate file called a source file that had the same base name, utils, but .c. All right, that's a source file, just like the main.c or whatever, like loan.c, just like the files that we've been working with up to this point. Then you can compile your library, not link, but compile your library into shared code using this -c flag. That compiles your code, but it doesn't create an a.out file. It creates an object file. In our case, it was a utils.o file. And just like on the system somewhere, there's a math.o file, there's a stdio.o file somewhere sitting on the system, already pre-compiled for that processor, for that operating system, waiting for you to link in and use that code in your main. And we did that by compiling our loan program along with the utils.o. And of course, we still had to put in the -lm flag because that was used on the CS50 IDE. Right? This is the order that worked on the CS50 IDE if you're using that stuff. Okay? So this can get very, very complex. And we're not going to get into it because it's kind of an advanced topic. But as you will see starting in your labs this week, when you start working with more and more source files, say that you have hundreds of source files, it gets very, very tedious and very, very error prone if you have to compile each thing with a single command every single time you have to type it out. So instead what we have is an entirely different programming language called make. And we've got these make files where you put in all these rules that to build this executable, it relies on these files over here. Well, how do you build those files? Well, there's another rule down below. That's how you build, and then it relies on these files. It relies on this other file over there. And you can have these hundreds of different dependencies that are all resolved by this make file. Now, to actually compile stuff, all you have to do is type make, and it does everything for you, as long as you've written the commands to do that in the make file. We're not going to get into it, but there is an extra README in your Xi books if you want to check it out on how to do basic make files. Otherwise, if there's ever a need to give you a more complex build kind of directive, we provide those make files, along with instructions on how to use the make files. All you have to do is read the handouts. But if you're interested, please go ahead and start reading about make files and start making your two. Any programming language is going to have some sort of a build system like this. In fact, make itself is language agnostic. It's just yet another programming language that you can specify rules for how to build stuff, the order and dependencies of all these files, etc. You could use it to compile Java if you really wanted to. We're not going to do that, of course, because this is a C course. Right? Some other miscellaneous stuff. A void function is a function that doesn't return anything. Just like in math, you can have a constant function. F of x is equal to 5. Well, it doesn't depend on x. So you can have a function without any input at all. And there's no output. There is no return value, right? The void keyword can be used to specify that a function does not return any values. You should still use the return, generally a void function, you should still use the return statement. It's just that you won't return anything. So what does that look like? it's return, and then the semicolon. Well, what did you return? Nothing, right? But no return value is specified. So you can have void functions. You can also define functions that don't take any input at all. They're not too useful, so I'm not going to show you an example, but you could, of course, define it. Like you could say int foo, and then there is no input, right? Dot, 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 whatever you're going to do in that function. There is no input because they're empty parentheses. When you call that function, you would not give it any input. Maybe it would do something and then return a value. Or maybe it would do something and then not return anything. It'd be a void function that doesn't take any input. It's not all that useful, but I should mention that you can do something like that. Okay? So what I want to do now is I want to take a deeper dive. How do these functions actually work? Okay? Now to do that, I want to show you this kind of toy program where I've got a function to add two numbers together, two integers together, and return the result. I've got a function to multiply two numbers together and return the result. And I've got this function called add squares that takes two numbers, multiplies a by itself, so that's going to be a squared, multiplies the other number by itself, so that's going to be b squared, and then it adds them together by calling this other function add. Right? And what I've got in here is 10 and 20. So if I were to add the squares, it would be 10 squared plus 20 squared is going to be what? Math majors. 10 squared is 100. 20 squared is 400. So added together should be 500, right? Now if I compile this and run it, what do I call it? Demo. You'll see that it is indeed 500. Now, you would never, ever write these three functions. These are just toy functions. If you actually wanted to compute this, of course, you would write it out. A times A plus B times B, right? You wouldn't put these into functions. I'm just showing you these functions so that we can look and see how they actually work under the hood. And I've got a visualization tool over here. This is pythontutor.com, but it supports multiple languages, in this case C. I took that program over here and I visualized it. Right? So what we're going to do is we're going to step through this program step by step and see what happens here. Okay? So you'll see over here, let me go to the next line here. So you'll see over here that we've got this thing called a stack. I wonder what that is. And this is main. Well, this is because it's the main function, right? Now in main, you've got a bunch of variables. In particular, we've got argc and argv. Those are the command line inputs. We're ignoring those for now. But we've also got these local variables. Remember, if you create a variable inside of a function, it's local to that function. Its scope is within that function. It only exists inside that function. Okay? So let's go ahead and step another step here. And what I've done is I've initialized A and I've initialized B to 10 and 20. I've stepped beyond lines 20 and 21. And now I'm about to step into line 24 here, which makes a call to add squares. Let's understand what's going on under the hood when we actually step into that function. Did you see what happens? Something new is created right here. It's got a heading of add squares. It's got its own A, B, and X, and Y. Why? Because you've got parameters A, B, and local variables X and Y. Right? These things are called stack frames. They're frames. It is a frame for, just like a picture frame. You are putting, you're creating a frame and then you're putting whatever belongs to main inside that frame. Well, when you call another function, you are creating a brand new picture. You're creating a new frame and you're putting everything that involves that function into that frame. I've got two variables named A, right? I've got two variables named B, right? I've got A up here and I've got A down here. But are they the same variables? Is that A the same thing as this A down here? Nope. Why? Because they're in different pictures. They're in different frames, right? That A is that A. That A is that A, right? So let's go ahead and step into this function here, all right? So add squares, we received values 10 and 20. Why? Because we called it with 10 and 20. Now what we're going to do is we're going to step into that multiply function, but we're going to pass it just A. Let's go ahead and go and step into that function. And you see that we've stepped into this multiply function that takes A and B. And When we step into that function, you'll see that since we passed a twice here, 2 copies of a, 10 and 10, are passed into this multiply function. This is yet another stack frame. So the idea here is that a function calls a function, calls a function, calls a function. You can do this as many times as you want, and each one will create a new stack frame, a new scope for variables to exist in. This a up here is not the same thing as this a down here, and it's not the same thing as this a over here. Certainly, hopefully that's abundantly clear when you look at b. This value has this b has a value of 20. This b has a value of 20. But remember, I didn't pass b into the multiply function yet. Right? I passed 2 copies of a, 10 and 10. And you can see that this has a completely different value than these 2 other b's up here. Clearly, they are different variables. I may have 3 variables called a, but they're in different stack frames, they're in different scopes, and so therefore they are different variables. When I go ahead and multiply those 2 things together, then a return value is returned back to the calling function. What happens to this stack frame right here when I return out of the function? It's going to get destroyed. Right? Why? Because I don't need it anymore. Function A called function B called function C. Once function C is done executing, it returns back to whatever called it, meaning that that stack frame is then deleted. Right? And you can see it disappeared here. What happens when I call multiply again? I call it with 2 different variables. This time 2 copies of B, and it receives 20 and 20. Okay? And again, it computes their square. The 20 times 20 is going to be 400. And it returns back to the calling function, returning 400 right here, destroying the stack frame that was created by calling that function. We continue. I'm going to call now add. I'm passing in 100 and 200, and 400. And you'll see here again that they're A and B, but they're completely different A's and B's. And hopefully that I drive home the point absolutely here that these are different variables when I point out that one is called X and one is called Y. They're in completely different contexts. Okay? They're in completely different stack frames, completely different scopes. When this one gets done adding them together, 500 is returned, and 500 is ultimately returned to the calling function. And C receives that value. You saw all those stack frames getting destroyed, right? So main calls add squares calls add. When add is done, that stack frame is destroyed. When add squares is done, that stack frame is destroyed. When the entire program is done, well, it's not going to show it here because I end the program, but the entire program and its main is stack frame is destroyed. Okay? That's how functions actually operate in pretty much any programming language. You're going to have this this call stack that you're calling. Right? So again, programs have a program stack. All right? It is a LIFO, that is a last in, first out data structure. Now let's understand why it's called a stack first of all. In real life, what is a stack? No? Go to the, I don't know if you have dinner before or after this class, but say you go over to the dorms, right? What do you grab before you grab your food? Hopefully something to put it on, right? What? A plate. Where did you grab the plate off of? A stack of plates, right? Now, when you grab that plate, did you grab the one at the bottom of the stack? No, why? Because then all the plates will fall off. If you say that you washed all the dishes and you have a clean plate and you want to add it back to the stack, where do you put it? Back on the top. Do you put it in the center somewhere, shoving all of those dishes off? And I think that they're probably plastics or melamine or whatever, so they don't break. But you're shoving them off the stack. A stack is an organized pile of stuff where you're only allowed access to one end. You can take something off the top. You can put something back on the top. That's called pushing and popping. In a stack, you can add something to the top. This is called pushing, right? Or remove something from the top. This is called popping. popping off the stack, right? But not in between. All right, you can't do it at the bottom. You can't do it somewhere in the middle of the stack. Otherwise, you risk shoving all those dishes onto the floor, right? So that's why it's a last in, first out. If I stack named dishes, A, B, C, D, what was the last dish that I just put on the stack? D. So what is the first one if I take a dish off the stack? What's the first one I take off? The last one that I just put in, D. I can go E, F, G, but I can't suddenly grab A, right? I would have to pop everything off to get to that bottom stack, that bottom dish, right? That's the idea of a LIFO data structure, right? You only interact at the top. You only interact with a stack at the top. Now, in the visualization over here, our stack grew down. That's okay. Just imagine taking this visualization here and turning it upside down, and now you've got the stack that corresponds to the real world. It doesn't really matter, right? There's no orientation of the metal and the electronics that are going on inside your computer. If you turn your computer upside down, it's not like things are going to spill out and the dishes are going to fall over. It's just a visualization tool, a way to understand it, okay? All right, there is no middle retrieval, right? So every time a function is called, a new stack frame, a new dish, is created and placed on the top of the call stack or program stack, okay? All local variables and all parameter variables, right? A and B, the parameter variables, and the local variables X and Y that we created, etc., are allocated and exist only inside the function's stack frame, right? When a function is done executing, its stack frame is popped off the top and control is returned to the calling function. That's why we use the keyword return, right? We're returning to whatever function called us, right? And possibly returning a value to it. All variables inside in the stack frame are destroyed. And I'm putting that in quotes there. They're destroyed. You cannot rely on them. You can't think that they're reliably accessible anymore. They may or may not be in memory. It depends on the operating system and how it operates and how it works under the hood. But certainly within your program, for all intents and purposes, they're destroyed. You can't have them anymore, right? The internal local variables that you had are all gone. The only thing that you have when you come back from a function is the return value, okay? And there's only ever one of those. So what I want to do is I want to propose a question, right? Or pose a question, I guess. So can a function swap values passed to it? So let's test this out. I'm going to go ahead and get rid of this example and this example. And I've got a swap program right here. We're going to try to write a function that swaps two values. I've still got A and B here. I print them out, and of course it'll be 10 and 20. I want to write a function to swap them around so that it is 20 and 10. And then when I print it out, I should expect it to be 20 and 10. So let's go ahead and try to write that swap function. It's going to be a void function. It's not going to return anything. So here's an instance in which a void function, sure, that's fine. It's not going to return anything. Let's call it swap, right? Because that's what it is. It's going to take two variables, A and B, right? And it's going to try to swap them, right? In fact, what I'll do is I'll print A and B inside the function to show you that I received 10 and 20. And then at the end of the function, I'll print them again to show you that I have successfully swapped A and B. Now, how do I go about doing that? Well, the first step is to create a temporary variable called temp. Put the value of A into the temporary variable. That frees up the variable A to take on the value stored in B. B, now I can put that temporary variable back into B because B has now been copied over. There we go. All right. what I'm going to do is I'm going to call this function now, swap on A and B. And I'm going to go ahead and comment out this last print statement. All I'm going to do is show you that, in fact, I have successfully swapped A and B from this function up here. Okay? GCC swap. There we go. All right. There's the first print statement inside the main, 10 and 20. Here's the second print statement when I go into the swap function right here, 10 and 20. It received the values 10 and 20. It then went through and swapped them, and then it printed out, and so I see 20 and 10, right? It was successful, right? Okay. Well, let me restore this print statement here and see if it actually did swap them. Okay. What is your prediction? Did it swap them or not? Probably not. Why? Because this is its own function, right? It has its own stack frame. It has its own A and B variables. Right? So let's go ahead and try it. Oops. And see that the original values are still 10 and 20. So once again, let's go ahead and copy this over to the visualization and check out and see what it looks like. Again, if you want to play around with this tool yourself, it's pythontutor.com. It was originally written for Python, but you can use it for C here. All right. It's pretty much, I think it has support for multiple languages. So let's go ahead and go through this. All right. So we've got 10 and 20. By the way, the emoji here, the poop emoji, is for an uninitialized pointer. It's their little joke, right? Nothing was passed as a command line argument, so it ends up being garbage. Garbage in emoji is apparently the smiling poop guy. Right? So I've got 10 and 20 here. Again, it's their little joke. Right? All right, so we call this swap function, and it creates a new stack frame, receiving the variables 10 and 20. But is this A and B right here the same thing as this A and B right here? Nope, they're in completely different frames. So when I go through the process on lines 7 through 9 of swapping them, temp gets 10, B20 is copied into A, and then temp is copied back into B. What have I swapped? I've swapped these parameter variables in the swap stack frame. Have I swapped these original variables up here in the main? Nope. That's why when I come back to main, A and B have not been changed, right? That stack frame in which I swapped those variables, it's destroyed, it's gone. Right? The original variables, A and B, are left as they were. Now to drive home this point, let me go ahead and go back and select different variable names, X and Y, and then X, Y, X, Y, X, Y, X, Y, X, Y, and X, Y, and then A and B, and I think that we're good there. You compile, right? There was a question while we're waiting for it to compile. Yeah, go ahead.
So, is this where an ampersand comes in?
The pointers will be our solution here in a moment. Yep. Okay, so let me go ahead and run through that code again. A and B have values 10 and 20. When I call swap, it should be absolutely abundantly clear now that X and Y are completely different variables. They don't even have the same names anymore, right? They are in completely different stack frames. So when I swap around X and Y, big deal. A and B are completely untouched. Okay? So what I need to do is I need to introduce a new concept. So can you swap values passed to it? No, because the values, or the variables, are passed by value. What does that mean? Right? By default, yeah, let me go ahead and go into another subtopic here. So how are parameters passed to functions? By default, variables are, like I said, passed by value. That term means that when a function is called, the values or value stored in a variable are copied and passed to the function, right? The parameter variables are completely different variables. they receive I before E except after C, so receive copies of the values of the original variables. Right? Therefore, any changes to the variables inside the function are not seen by the calling function. Our swap of x and y, because main didn't know anything about x and y. The swap of x and y and those x and y variables get destroyed once you return back to the calling function. Right? So if you really, really want to write a function that changes the values of the variables in another function, you need to pass them differently. Right? Instead of passing by value, we pass by reference. Right? Reference. Right? So the idea here is that pass by reference will pass memory addresses of the variables instead of the variables' values. Oops, sorry. So this is getting into the almost the bare metal of your computer. You can actually manipulate actual memory addresses in your computer and get access to that low-level kind of hardware stuff. Instead of passing in A and B, copies of 10 and 20, I actually pass the variables themselves. That original A variable is stored at memory location XYZ. That variable B, that's stored at memory location DEF. If you want to, you can jump to those memory locations and start manipulating them. Start screwing around with them and do whatever you want to them because it's your memory. Right? As with Spider-Man, with great power comes great responsibility. So directly manipulating the memory addresses of a computer, that's a very, very powerful thing. You have to be very, very responsible about it. Right? Otherwise, if you start messing around with the actual memory and start screwing it up, then, well, you end up screwing up your own memory. Now, if you end up screwing around with some other program's memory, then hopefully the operating system will detect that and say, nope, you're not allowed memory over there. Program A should not be able to mess around with program B's memory. If so, that causes a segmentation fault. The segment of memory that doesn't belong to you, you're trying to access it, you're trying to change it, you're trying to muck with it. Nope, that's a fault. You cannot do that. So it ends up with a segmentation fault. And where have you seen that before? With scanf, if you forget the ampersand, right? That should tell you that the ampersand is involved in getting the memory address of a variable. Okay. So to do all this, though, first of all, we need pointers. A pointer is a reference to a memory location. It points, like with a finger here, it points to a memory address. Okay. So how do we do this? Pointers in C. So what I'm going to do is I'm going to go back over to my code here and go over to the demo. I'll keep swap over there. I don't need any of this stuff anymore, so let's go ahead and get rid of it. I don't need this stuff anymore. So I will eventually incorporate this into the notes. But here is a regular old variable declaration. Int x is equal to, say, 42. Okay? That's just a regular old variable. Right? Let's create a pointer variable. Right? A variable that can point directly to a memory location instead of an actual value. Right? Now, the idea here is that memory is made up of two things. It's made up of an address, and it's made up of content. Right? And unfortunately, I don't have a visualization all ready to go here. I'll pull that up next time. But if you read, if you check out the book, no, we'll check it out here, and I'll show you a visualization of this later. But basically, think of an address like a home address, right? Your address is 1234 A Street, right? But that's not you, the variable that lives in that address, lives in that house of that address, right? The person that lives in that house, that's the value of the variable. The address just tells you where to find that variable. So you've got an address and you've got the contents of the memory. You've got an address, you've got the people that live in the house. You've got the value that lives in that house, right? So how do we create a variable that can point to a memory location? What I'm going to do is I'm going to use the star operator. The ampersand will come later here, right? This is going to be a pointer to x, okay? This creates a pointer to an integer, right? The above variable, pointer to x, is a pointer variable that can point to any integer value, right? So bad things will happen if we start pointing it to other types of variables, right? I'll show that to you later on here. But pointer to x does not necessarily point to anything at this point, right? So let me go ahead and copy this over to our no, I'll do this. I'll do it here, right? So at this point, what does x pointer to x point to? So what is it pointing to? Nothing? Nothing? Null? Who knows? Right. Well, let's ask this C-tutor visualization over here. Right. I'm going to go ahead and get rid of swap. And I'm just going to put in the code that we have right here. So let's visualize this execution. Hopefully it'll be fast since it's only 2 lines of code. There we go. So I've got x. Oh wow, cool. It realized I never even used that value, and so it compiled it away. Not cool because it's not actually visualizing it, but whatever. All right. So the compiler here is going a little bit farther than I wanted it to, and took that variable and threw it out. You didn't do anything with it, so you don't need it, so I'm going to not even do it. So what does it point to? Nothing, null, who knows? Who knows? Right. So if I create a variable, let me go back up here, y, int y. What value does y hold right now? Is it necessarily 0? 99 times out of 100, it's going to be 0. But is it necessarily? Nope. It's whatever, might be whatever that was there to begin with, right? Whatever was in that memory location that was left over from the last execution or something like that, right? Likewise, with a pointer variable, it can point to an integer, but what does it point to now? We have no idea. It could be one of many things, right? It could be null, right? Null is a special variable. This is the null pointer, the pointer that points to nothing, right? It could be some random memory location that belongs to us, right? And so that we would end up screwing up our own memory if we tried to do anything with it. We could, corrupt our own memory. There we go. Or it could be something else. It could be a random memory location that doesn't belong to us. And if we tried to do anything with it, it might result in a seg fault, segmentation fault, just like forgetting the ampersand when you use scanf. Right? So how do we make it point to something? Actually, let me give you another term here. Pointer to x is an uninitialized pointer, and working with it will result in undefined behavior. Undefined behavior, anything goes, anything can happen. In fact, there's a joke C implementation that nobody would ever use, but it's written so as a teaching tool to remind you that undefined behavior is undefined behavior. Undefined behavior is dangerous, because what it does is, in the event that undefined behavior happens, that it's something that the C language doesn't define. What happens under these conditions? I don't know, whatever you want to happen. And so what the C compiler has been created, the C system has been created, so that once, if you ever do any undefined behavior, it deletes the hard drive. Right? Now, of course, that's super, super dangerous, and nobody would ever actually use that in practice. but it's used to illustrate that undefined behavior is extremely dangerous. You can't guess. You can't make any assumptions about what happens when undefined behavior happens. Hopefully, it'll just kill your program with a segmentation fault. Hopefully, it doesn't delete the entire hard drive, right? So be careful. It's undefined behavior. You can't say anything. You throw up your hands and say, I don't know, right? So how do we make it so that it's a valid pointer? You can make pointer to x point to null, N-U-L-L, all caps like this, using, well, the keyword null. So let me go ahead and give myself some more room here. Pointer to x, I'll set it equal to null. Right? And you can also check for null. You can check if pointer to x is equal to null, then refuse to do anything. Printf safety issue cannot do anything with a null pointer. Right? There we go. And we'll see, and I'll give you a way to remember that you need to remember that you need to handle null pointers maybe by the end of today. Okay. Anyway, so you can check for null by simply checking this equals equals. NULL is all caps. It is not the same thing as NULL with a capital N, lowercase n. It is not the same as NULL, all lowercase. Those are not defined in the C programming language. It has to be all caps null. Okay. So you can make it point to null, or you can make it point to something valid. You can make pointer to x point to x as follows. So pointer to x is equal to x. Now let's think about that for a second. This is not the correct way of doing this. A pointer to x is equal to x. What is that doing? It's assigning what was stored in x? 42. So what does pointer to x equals x mean? It makes it point to memory location 42, right? So the following makes pointer to x point to memory location 42, right? The value stored in x. Right? Is that going to be valid? No. Probably not. I mean, who knows if the memory location 42 even exists? Even if it does exist, does it belong to you necessarily? Probably not. Right? That's just some random memory location. If I go ahead and compile this, it's going to be a warning. Right? Safety issue, cannot do anything with a null pointer. Right? And if I try to do anything with it, it's going to be a segmentation fault. And we'll see how we'll see that here in a second. But how can I make pointer to x point to x? Pointer to x is equal to x. That's not it. What I need is a memory location. The thing on the left-hand side is a pointer. It is a reference to a memory address. The thing on the right-hand side is not the memory location. It's not the address of the house. It's whatever's in the house at the time. So how do I make these two things compatible? I have to convert x into a memory location using the ampersand. Right? The ampersand in front of a variable is the referencing operator. Right? It gives you the memory location of that variable. Remember, x is just a regular old variable. You store 42 in it. You store 59 in it. You store 8 in it. Whatever you want to store in it. Those are values. But a pointer to x, that's a memory location. Okay? So let me show this to you and see, and you can see what it looks like. I'm going to print out the values here. So pointer to x points to memory location. Now I'm going %d. That's not how you get. That's how you format a what kind of integer or what kind of variable? An integer, right? So how do you think you format a pointer? Pointer p, right? It's stored at memory location p, and I'll go ahead and print it out. Pointer to x, and printf. The value stored at x is, and then here I will print out the value x, which is still 42 because I haven't changed it, right? And this will be x, okay? Now let's go ahead and run this again. Again, it's going to be a warning down there because that's not proper, but it will run. Pointer to X points to memory location 0xFFC or 7FFCA2CC601C. Is that meaningful to us at all?
No.
Nope. It's just some memory location sitting on Amazon Web Services servers somewhere on a virtual machine, right? With 10 different layers of abstraction between the actual, hardware down at the bottom that is stored on some node, I don't know, in St. Louis or something like that, right? And if I run it again, will I get the same answer there? By the way, the value stored is 42, right? Because we haven't changed it. Should I get the same value if I run my program multiple times? No, it changes every single time. Why? My program is being loaded. Oh, yeah, go ahead. Oh. Exactly. The entire program stack frame gets deleted each time and recreated every time I run it. So it gets loaded up in a different location in memory every single time. In fact, if you got the same memory location between 2 different runs, you got really lucky. Go out and buy your lottery ticket because it's up to $450 million or something like that, right? You've got some luck going right now. By the way, they didn't cover, so I'm glad I didn't make that bet. The Huskers, that is, or the Oklahoma didn't cover, right? So anyway, I never have any luck, and so I'm never going to see this being loaded up in the same memory location. Okay. What happens if we do something like this? Let's go ahead and take these print statements here. And if I set it equal to X, the memory location 42, it's going to say that it points to a certain memory location. What's stored at that memory location? So again, let's go ahead and run it, recompile it and run it. It's probably not going to end up as a segmentation fault yet because it just says that it points to memory location 42, right? Which in hexadecimal is 02A, if you want to convert 42 to base 16. But you didn't actually do anything with it, so it's okay. It's only when we touch that memory and start to manipulate it do things go wrong. So how can we manipulate it, right? You can change the value in X using the regular old assignment operator. So instead of 42, we'll go ahead and go to, what was the score again? 22 to, and they, okay, whatever. 101. There we go. X is equal to 101. And we'll print it out again. And you'll see that this is perfectly fine. Because again, we're only changing it through its regular old variable. But what I can do is you can change the value of X through its pointer. So what I'm going to do is pointer to X is equal to, now I need a third number to show you that it's actually changing, 17. All right, there we go. Pointer to X is equal to 17. Now that, remember, that's invalid, right? That's basically like doing, what was it? This up here, changing it equal to 42. So what I want to do is I want to change the value stored in that memory location. Sorry, that's going to be the star operator, right? So star pointer to X is a dereferencing operator. It changes a pointer variable into a regular old variable. Right? It's just the opposite of the ampersand that we did up here. I took a regular old variable and changed it into its memory location by putting an ampersand in front of it. I took a pointer variable and put a star in front of it, and changed it into a regular old variable to change it to the value 16, or 17 in this case. It's not even going to print. There's going to be a segmentation fault at line 56, because that memory location, which is now 101, does not belong to you. Segmentation fault. This line right here is causing it. We don't even get to these print statements here. Because what you tried to do is you tried to go to memory location 101, right? That's what was, 42, right? You tried to go to memory location 42, and you tried to change the contents. You tried to move somebody out of their house and move somebody else in. You tried to move 42 out and 17 in. That memory location doesn't belong to you. It's just like breaking into a house, right? The house doesn't belong to you. That's illegal. In this case, the operating system or the cops, and they say, no, you can't do that. So we're going to kill your entire program with a segmentation fault. Right? That segment of memory doesn't belong to you. Therefore, you cannot touch it. Right? You can't print what's there. You can't change what's there. You can't do anything with the contents stored at that memory location. Segmentation fault, it detects it. Now, a bad operating system or an operating system with a flaw in it may not detect this, in which case you can write a program that then goes and gets access to memory locations that don't belong to it, and then you can steal stuff. Right? For example, you could write a program, if there was no detection at all, you could write a program that went and read the memory contents of your web server. And on your web server, a whole bunch of passwords were stored in plain text in memory, right? And now you can start scraping that and grabbing all that information, sending it on to wherever you want. A good operating system would say, no, you can't do that because you can't access memory of another program because that's a security issue, right? And it's happened before. The flaws like this happen all the time. Heartbleed, if you remember that from several years ago, was an attack vector like this, where you could get, basically you could randomly access memory that didn't belong to you. And if you did it over and over again and you check for passwords, you check for SSL keys, that's secure socket layer keys, encryption keys basically, and you tested it, and okay, I didn't see any keys there, try it again. I didn't see any keys there, try it again. You tried this over and over and over again, and eventually you got to some random memory location that did contain that kind of sensitive information. Right? And that's a common attack vector. A good operating system will detect that and say, nope, segmentation fault. A bad operating system or a program with a flaw in it would allow you to do something like that. Right? So it is definitely a security issue. And again, it goes back to what I said. With great power comes great responsibility. That is the most powerful of all, getting access directly to memory locations that don't necessarily belong to you. Right? All right. So that's the referencing operator. So this begs the question, why would you ever want a pointer when you can directly change the value of an integer, of a variable, using the regular old assignment operator? I don't need to change the value. All I need to do is say x is now equal to 17, right? Why would I need an actual pointer? So that I can pass it to a function. Let's go over here back to the swap. This swap is giving you a and b by value, right? In other words, 10 and 20 are being copied onto the program stack, and that's what's being given to you. We can rewrite this function so that it's swapping by reference instead. So instead of giving you 10 and 20, it actually gives you the variables a and b using the memory locations. This one's stored in memory location XYZ. This one's stored in memory location DEF. You can then jump to those memory locations and manipulate the contents of that memory. Let's see what that looks like. So instead of passing a variable, we pass in a pointer to a variable for both of these. By putting a star in front of it, you're not passing in a regular old integer anymore. You are passing in a reference. You are passing in a memory location. You are passing in a pointer variable, right? And we can print those out, but we can no longer treat them like regular old variables. How do I take a pointer variable and change it into a regular old variable so that I can print it out? Dereferencing operator, which is what? The star. Good. Now, I can create a regular old variable temp to grab the and put it over here. 10 goes into temp. But the thing on the left-hand side is a regular old variable. The thing on the right-hand side is a pointer variable. So I do the same thing. I go with a dereferencing operator. Likewise, dereferencing operator, and dereferencing operator. Do I dereference temp? Nope. That's a regular old variable. If you dereference a regular old variable, the wrestler Bret Hart will come after you and clunk you upside the head. You'll understand that reference by the end of the day. Right? So don't do that. Right? Let me go ahead and show you that indeed they have been swapped in that function. Now let's come down here, and we won't call that swap function anymore. We'll call swap by reference. Okay? Now let's try to compile this first of all. It's going to complain, right? Because swap by reference is of type int star, which is, now we know, is a pointer. But we give it a regular old variable. Down here is a. In main, is a pointer variable? Nope. Is b a pointer variable? Nope. They're regular old variables. So how do I take regular old variables and make them into pointers? What was the opposite of the star? The ampersand. Right? And now I'm passing in a and b to the swap by reference. And it will consequently change those two. So let's go ahead and compile this. No complaints anymore. And when I run this, now it is swapped. 10 and 20 before, 10 and 20 when it gets into the swap function, 20 and 10 before it leaves the swap by reference function, and 20 and 10 when it gets back from that function. Once again, let's look at the visualization of this thing. All right? And you'll see that the visualization here, they are literally pointers. It's just an arrow pointing to a memory location. Right? And next. So A and B, we print them out. Now we go into swap by reference. Right? A and B, you see right here, they're called pointers now. Up here, they were regular old integers. Int, they're kind of small if you can't see them in the back. But int, you'll be able to see them on the live stream. And then I've got a pointer here. Now let's go ahead and jump into this function, and you'll see that they are literally pointing up that direction. I don't think I can move this stuff around. But you'll see that this pointer, when I highlight it in red, B is pointing to that integer. A is pointing to that integer. They don't hold values. They hold references to values, references to memory locations. So when I swap them around, 10 gets put into temp. I then jump to the memory location so that I can put 20 into A. I then jump to the memory location so I can put 10 into 20. Print them out, and you see that they are indeed swapped. Then when I return back, those pointers are destroyed, and I'm left with the swapped variables now. Right? So this is very powerful. What I can do now is I can pass in variables, and the function can actually manipulate the contents of that memory location. Right? Okay. Any questions so far? No? Okay. Let's see. Oh yeah, I'm going to make sure that you have all of this in the notes, all of this demonstration code here. There we go. And pointers in C. There we go. And all of those notes are now will be pushed to GitHub here after we're done. All right. All right. So this should look familiar, right? Ooh, did I do it right? Yeah, there we go. I've got an extra. There we go. So observations. When we used scanf, right? Let's say just say %d and then %x. We used the ampersand to pass in x by reference. Why did we do that? So that scanf could read the input and place the value into the original variable x. Right? What if we just passed in x by value? Whatever was stored in x, 10, would have been passed to the function. The function couldn't do anything after it read the input, right? In this is where I come up with the following analogy. Passing by reference essentially passes a bucket to the function. That bucket, with the bucket, the function can put stuff in, take stuff out, etc. If I don't give you a bucket, if I just give you 10, well, you can change the value 10, but do I know anything about that? Nope. But if I gave you a bucket that we both shared, right? You can take stuff out of the bucket, you can put stuff back into the bucket, and I still have access to the bucket. When you're done operating, that bucket comes back to me, and I can see what you put in that bucket. So I'm basically passing a bucket to the scanf function. I'm saying fill this bucket with whatever input you read from the user. Right? And I'm only able to do that if I pass by reference using the ampersand. Okay? Manipulating on initialized variables, or even null, or invalid pointers will lead to a segmentation fault. Right? Remember what Bret Hart says. Right? Anybody know who Bret Hart is? No? All right. And we're going to find out. And I don't know if here, let me turn on my audio. So we're going to have to go to YouTube for this. YouTube, Bret Hart, dereferencing a null pointer. So Bret Hart was there we go. Bret Hart was a wrestler from the 80s and 90s. And here he is. And again, I don't know if this is going to work or not. Let's find out.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
Okay, so I guess he didn't hit the guy over the head. But remember that Bret Hart was debugging and told you what was wrong with it. So hopefully you'll remember that. But it was just a promotional video that was put together when they were building some wrestling game in the 90s. And so, of course, they sent the wrestlers out and they interacted with all the developers. And they had all those stupid little jokes like that. Always remember that if you dereference a null pointer, you're going to have a bad time. Right? So, for example, if I've got int x, int star p, right, and I set that equal to null, how do I get what's stored in null? Printf. P points to %p. What do you think null points to? What the value of null is, first of all? This won't crash because null has an actual value. What is it? Nil, 0, right? It's some internal value. And what's stored in null? Null stores %d, let's say, right? And the line. And let's dereference our null pointer. Let's go ahead and do what Bret Hart tells us not to do. Right? I have dereferenced p, which is null. So what's going to happen? Hopefully somebody comes out of the screen and knocks you in the head, gives you a segmentation fault. Right? Don't do that. If you create a pointer, it's a good idea to initially set it to null unless you know exactly what you want to set it to immediately. Right? Check for null. If you're ever given a pointer, before you muck with it, before you look and see what's stored at that pointer location, before you go and put something into that memory location, make sure that you are checking for null. And if it's null, then don't do it. Right? Just like if you're about to divide by x, maybe you should check, is x 0? Then don't divide by it. Don't divide by 0. This is basic error handling, which is what we're going to talk about next. But summary, first of all. Let's see. Yeah, I'm going to go back to our notes over here. Okay. There we go. And by the way, if you do post on Piazza, what's going on? I've got a segmentation fault, and we look at your code, and we see that you're that you're dereferencing a null pointer. I'm going to post that video as my answer. So, summary of pointers. A pointer is a memory address of a reference to a memory. It's a reference to a memory address. A pointer variable can be declared using the star operator, right? Int pointer to a. It's best to initialize pointers, at least make them point to null, or make them point to something valid if you know what you want them to point to immediately. To make a pointer variable into a regular old variable, you dereference it using the star operator. To make a regular old variable into a pointer variable, you use the referencing operator, which is the ampersand. Right? And finally, the last thing I'll mention today is don't make pointers point to things they shouldn't point to. Right? And for that, I'm going to go back over to my code here. And let's go ahead and create some variables, regular old variables. Right? Double y is equal to 3.14. Right? And let's create a pointer variable. Int star p is equal to ampersand y. What have I done there? What kind of pointer is p? It's an integer pointer. It can point to an integer. But what have I made it point to? A double. I wonder what's going to happen. Printf p points to memory location %p and the line p. Printf what is stored there? %d or p or %lf or f, I should say. And let's see if either one of those works. There we go. So how do I make sure that I dereference it so it's a regular old variable so I can print it? Star p and star p. Right? Now in this first one, I'm going to try to format it as an integer because that's what it is. In the second one, I'm going to try to format it as a float because, or as a double because that's what it's pointing to. Are either one of these going to be correct? Let's find out. Warning, oh, error. Comma, thank you. That has nothing to do with pointers. That was just me fat fingering it. There we go. Now I am going to get a whole bunch of warnings, but no errors, so it'll run perfectly fine. But will it give me the answers that I'm looking for? Both of them are nonsense. Are either one of those 3 or 3.14? Nope. You have made an integer pointer point to a double. Do you remember how many bytes an integer takes? 4 bytes, 32 bits, 8 bits per byte, right? How many bytes does a double take? It's in the name, double the number of bytes, 8. I've made a pointer that's supposed to point to 4 bytes. I've made it point to a memory location that has 8 bytes. So effectively, it's only taking half of that number and trying to interpret it as an integer. Whatever garbage that happened to be, apparently, if you treat it as an integer, it's this number here, 13743895535, which has nothing to do with 3.14. When I try to treat it as a double, right, then it's looking at the other 4 bytes, which are all 0, right, and so it ends up being 0. Right? This is just garbage. Right? Make sure that if you've got an integer pointer, it points to integers. How would I make it point to, how would I make a valid pointer to y? Make a valid pointer to y. What kind of a pointer variable would I need to create then? A double pointer. Double, I don't know, PQ, because that's what's next, right? And I'll make that point to y. To y, oops. Y, there we go. And let's go ahead and see if that works. Q points to memory location Q. What is stored there? And of course, I won't interpret it as an integer anymore because it's properly a double. But I will dereference Q, and you can see here that it will actually work, and it'll preserve that 3.14, whatever it was. Right? There. It's pointing to the same memory location as P is, but now it's being treated correctly. It's being treated like 8 bytes total. And the 3.14 is preserved. So if you've got pointers, you need to make sure that you are pointing them to the correct variable types. An integer pointer points to integers. A double pointer points to doubles. And a character pointer, a char pointer, should point to chars, right? And all of these things give us the basis for the next topic that we'll get to in a couple, like maybe 2 weeks, which are arrays, right? And collections of things, okay? So I'll make sure that you have this in the notes. Otherwise, we will get plenty of practice with pointers in the next couple of weeks. Right? So, see, there we go. No questions? All right. Then I will see you on Wednesday.